this, I apologize if this some of the material I'm going to talk about you already know. I'm not quite sure about the sort of backgrounds of various people here. So it's going to be a much more sort of introductory talk than Jitendra's, but I will go into a bit more detail, okay? And so do please ask questions as I go, okay? And I'll do my best to answer them. Okay. Oh, wait, no, I thought that was a question. All right. Okay. So now I'm going to talk pretty much exclusively about convolutional nets. So here's a picture of Jan LeCun, who's invented them. So you can think about these essentially as a neural network with just a specialized connectivity structure, which I will talk about in a moment. And that makes it particularly appropriate for tasks involving images. Now, the sort of plain vanilla version of the ConvNets, which I'm really going to talk about today, are really designed in some sense for sort of classification or regression problems. We were going from the image to some sort of low-dimensional output, like a class label or something, or some sort of number, some location or something like that. Okay, so some of the models Jitendra talked about, which people have developed subsequently, might output some kind of image as well. But that's a sort of I guess a more modern extension to these models. Okay, now the second thing I also want to just say is that within deep learning, ConvNets of course really form just one particular model. So I guess for us, in computer vision, sort of ConvNets are sort of synonymous with deep learning, but actually just to point out that there is really a kind of little universe out there of things that people think about in the deep learning community, and particularly when you're thinking about these more modern things to do with unsupervised learning, there's a whole series of things like stacked autoencoders and so on and so forth. But anyway, we're just going to today just talk about ConvNets. Okay, so I'm going to give a little bit of a brief overview. It's going to have some slight overlap with what Jitendra was saying earlier, and then we'll go down to the nitty-gritty and just look at all the different pieces of the whole thing. So just to give you an overview, the model's really going to consist of a series of repeated layers, and in each layer you can think about there's a sort of convolution operation, and the filters, those convolutional filters are the parameters of the model. That's what's going to be learned. There's some kind of element-wise non-linearity that's applied to the elements of the feature map, so all this I'll explain in more detail. And then there's some kind of pooling operation, which is a kind of spatial aggregation that takes place. And that gives you a feature map, and then you sort of take those feature maps and present them to another stack of these three operations, okay? And you keep doing this, and the effect, once you've done sort of several layers of pooling, the spatial extent of your feature maps will end up being reduced, and typically you'll expand the number of feature channels. That's why you see here. So initially we have reasonably high spatial resolution, but say 6 channels. This is an old figure from Jan's original paper. And after several stages, we end up with feature maps that are much smaller spatially, but say 16 of them. And at some point, you can then sort of just plug that into a fully connected network. Okay, so this is just a standard fully connected neural net. So the idea is you just take this and just treat it as just one big long vector, kind of ignoring the sort of spatial layout information that you had in the previous layers. Okay, and then so this is, you can think of it as just a classifier on top. And the idea is you're going to train this thing by taking your input examples, so your training examples for which you will have known labels. So you will take the input image, push it forward through the network, computing the convolutions and non-entry pooling, yada yada, multiple times, and you get some kind of output. You compare that output to your ground truth, get some error signal, and then you can back propagate it through all the layers, updating the convolutional filters that you're using. Okay, so that's the overview of the whole thing. So just to make this is the historical note that Jitendra was making. So this architecture wasn't invented out of the blue completely by Jan. There was just people thinking about these things for a long time, from the biological inspiration, people like Fukushima and so on. Okay, so just a little the history, which Jitendra alluded to. We're just going into a little bit more detail. So the ConvNets models, they were invented a long time ago, and they did work very well for things like these quite simple constrained problems. We had fairly simple images like these sort of handwritten digits, and also it's worth noting that these data sets, there were quite a lot of examples per class. So things like MNIST, did have like 10,000 for examples per class, which was actually quite a lot for when the data set came out back in the day. And equally, this is road sign recognition. So again, these are sort of pre-segmented images. All the task here is just to say which type of road sign it is. So in these types of domain, or these types of problem, the networks really did work very well. So they worked well before the sort of deep learning revolution that we're familiar with. But then when people tried them on sort of more realistic data, sort of natural images you might find on the web, in the early days of those using those data sets, the models fell over and just didn't work at all. And I think looking back at it now, one real issue was these data sets really had very few examples. So Caltech 101 had maybe sort of 30 training examples per class, and that's just too few to really train up these what effectively are very large models with many parameters. And that's but these sort of handwritten digits did actually have tens of thousands of examples per class, and so that's possibly one reason why they worked a lot better. And what happened was, I guess, in around in not, I guess it's a few years ago now, but around sort of 2009, 2010, the image computer vision community started to get its act together and start to compile these really quite large data sets, like ImageNet, which you have millions of images that were then hand-labeled by people on Amazon Mechanical Turk. And Jeff Hinton and his students, Alex Grzewski and Ilya Sutskever, took this data and effectively played around with these ConvNets and managed to get the two of them, managed to train them up and get some very, very impressive results. So the idea, the problem, to be precise, they were tackling is, given an image, you're supposed to just predict a class label. So in this ImageNet challenge, there's 1,000 possible classes. So you have to give, you have to say what you think the correct class is. Because their classes are somewhat ambiguous, the way the metrics scores things, you're allowed to sort of, if the correct answer is in the top 5, then it's deemed correct. So the correct answer here is, if it's correct, it's shown in red. If it's blue, if it's not. And this is the ground truth answer. So these are some examples from Alex Grzewski's paper. And you can see that even when it didn't get the right answer in the top 5, it still gives sort of somewhat reasonable responses to these images. Okay, and they're actually, so at the time this was really very impressive. So just to look at the actual architecture they used. So what was kind of interesting was it really was the same model that Jan had back in the day, but it was just bigger. So they had, instead of 3 or 4 layers, they had 8 layers, and they were using, now, 1.2 million images or something from ImageNet, rather than 1,000 images in things like the earlier Caltech data sets. And of course, you've got a big model, lots of data. You need to have a lot of computational horsepower to crunch that. And the GPUs really at this point were starting to give big speed ups over CPUs. So Alex Grzewski is actually a wizard hacker, so he was able to implement the sort of convolution routines and things like that extremely efficiently on the GPU, and so on. So just to give an idea, it really is actually a pretty big model. So it has about 60 million parameters. Most of them actually are at the top here in the fully connected layers of the model. This is a representation of the architecture, so you can see these are the sort of convolutions and the poolings multiple times and so on. And in those days, the graphics cards didn't have a whole lot of memory, so they actually had to split the training over 2 GPUs. And it took a considerable amount of time, but it did actually work pretty well. So this is a little historical plot of performance on this ImageNet classification benchmark versus time. So this is the pre-deep learning era. So this is the error rate here. So lower is better. And you can see that this was the winner of the competition in each year. And the performance here was sort of 28, 26%, that kind of thing. And then the Alex Grzewski, Sutskever, Jeff Hinton paper got about 16%. There's a big jump. And I think at that point, everybody was pretty impressed. And I think what was even more impressive was that that was just the start of it, and people subsequently found they're able to just play with the architectures of the model, not really changing anything else. The training algorithms were basically the same, and continue to get really quite dramatic improvements in performance. And you can see, so now it's down. In 2014, it was around about 6 and a bit percent. They did some person, I think it was. Alex Karpathy at Stanford did actually go through the data and have a go at seeing how he could do, and he got about 5% error. Obviously, it's a slightly weird task for a human to sort of give one out of these 1,000 categories. It's quite easy for a human to sort of get confused between some of the categories. And then, perhaps impressively, in the recent years, the last couple of years, the error rates continue to go down. So I think the winner of this year's competition was just under 3%. Error. So of course, this thing needs to be taken with a bit of a pinch of salt because it wasn't a really carefully controlled experiment, and it's a somewhat artificial task for a human to be doing anyway. But the key point is, it's gone from sort of performance here, which isn't really useful for sort of in practical settings, to performance which is really pretty impressive.
Rob, can you say a few
Sure.
words about what these tweaks that were done from 2012?
Okay, so I'm going to get to that. Yeah. So this is just the sort of historical overview, and then we'll get to the details. Okay, so these are just this is actually from. This is not perhaps a state-of-the-art model, but this is quite a decent one from a startup called Clarify. It's actually started by one of my students. So this is just some holiday snaps I took a year or two ago and just feeding it through the system. So because they're my holiday snaps, I know the model couldn't have trained on them. And you can see these are the top-ranked tags attached to each image. So you can see it's doing these ones are sort of fairly easy ones, and so on. So these, it's getting the things quite well. There's a few slightly strange things that are ranked highly there. It seems to think it's in Helsinki. And this was a hard example, so this actually turned out to be an underground cave but it bears quite a familiar resemblance to the Sagrada Familia in Barcelona, if you've ever seen that. So that's why the thing is thinking it's some kind of, Okay, so I should say these are examples from a system produced by some of my colleagues at Facebook. So this is actually an instance segmentation problem. So this is not just doing classification now, but sort of trying to segment each example. So these are just showing some of the typical images. This is from COCO data, to COCO evaluation, I think. So you can see that it's getting quite small objects, and then you can even handle quite complicated setups like this, where you've got many, many overlapping objects. And you can see that things can do a pretty good job of finding the sheep and so on. So these things models are working quite well. And Jitendra showed a nice example of sort of the latest detection, where you're putting bounding boxes and so on. Now, I think so. One thing is, so obviously the results on this ImageNet data set are pretty impressive. But I think what's even more impressive is the fact that the models that were trained on ImageNet, it turns out, don't just work on ImageNet. They actually seem to work pretty well on other data sets too. So if you take your model, train it on ImageNet, and all you then do is sort of chop off that classifier at the top and take the trunk from ImageNet, fix that, and then take your new data set and just retrain a little classifier on top of the existing trunk. It turns out that you can actually do very well indeed. So this is just, many people have found this. I'm just showing this on some sort of, from a slightly older data set. So this was Caltech 256, so it has a fairly limited number of training examples per class. These were some existing methods. So at the time we were doing this work, I guess a couple of years ago. And if you just try retraining, this is an ImageNet trained model. You just now retrain the top classifier just using the Caltech 256 training data, and this is the kind of curve that you get. Okay, so it's very impressive in the sense that with just 6 training examples, you're already beating, at the time, this was like 2013 or something, late 2013, the current state-of-the-art model. And so it's clear that the representation you've learned on ImageNet is generalizing to this other data set. And I think a lot of people have found this, that if you train on ImageNet, actually, you can get a pretty good general-purpose representation, visual representation that you can use for many other tasks. And so that's really very helpful indeed. You don't have to sort of get millions of examples in your particular visual domain. You can probably retrain with a much more limited amount of data in a model that was already pre-trained, as it were, on ImageNet. Okay, so that's the sort of little overview. So let's go back and do everything in a bit more detail. So let's look at the operations in each layer, and then how we how we pick the architectures and the training and all that stuff. Okay, so basically, you're going to be taking in pixels at the input. Later on, the input to each layer will be a set of feature maps. You will convolve those feature maps with the learned dictionary, pass through some element-wise non-linearity, and then do some spatial pooling. So I'm going to go through each of these 3 stages in more detail. Okay, so basically, you have the first layer. You have your image. You'll take your filter, whose coefficients you will end up learning through backpropagation, and you're going to slide that over the image to produce some kind of feature map like you see here. Okay, so gray is 0, white is positive, black is negative. And so, of course, you will have not just one filter, you'll have a whole set of these, so that you'll have then a different filter that will do the same, and that will give you a different feature map, like so. Okay, now there's a couple of important sort of assumptions that come into play here. So firstly, we notice we use the same filter, within each feature, with each channel, we use the same filter coefficients at each spatial location. Okay, and that's one assumption. The second thing is that for each element here, so say we pick this particular element, that corresponds to placing this filter, down in this position here. And the key point is that this is a local window, right? It's not like this element here depends on all the input. There's a sort of locality in the sense we're assuming somehow that only, for this element here, we can get away with just looking somehow at a small portion of the input signal. And that's, of course, a peculiarity that is not true of a general neural net. If you think about a fully connected neural net, every unit in the hidden layer connects to every element in every channel of the input. And that's not what's going on here, right? If that was the case, then the filter would be the size of the image. Okay, so just to dig down what's meant by that. So what you're really exploiting is the fact that in image data, these natural image data, the dependencies are somewhat local. Okay, so that is that what I'm showing here, in fact, is a sort of plot of correlations, spatial correlations, as a function away from the center pixel, just computed on CFAR 10. So you can see here that gray is sort of 0, and if you see anything that's not gray, then that's telling you that showing you there is actually a significant correlation. And what you see is that the correlations fall off very quickly. So in fact, at least on CFAR, which is a low resolution data set, then you can really only need to worry about sort of, say, 2 or 3 pixels either side of your current location. So that tells you can get away with a pretty small filter size in your network. Okay, and this is of course also true actually on more general image data. And the second thing to say is that we also, by putting the same filter down at all those different spatial locations, we're assuming that you have somewhat spatially stationary statistics, that the images sort of look the same at different positions within the image. And that is sort of true. It's not actually exactly right. And then there's a nice paper by Antonio Traub and Aude Oliver some while back where they looked at looked at this kind of thing. So this is looking at sort of power spectra, the computing power spectra over local sort of pieces of the image. So this is spatial location. The little thing here is showing the shape of the power spectra. And this is for natural and man-made scenes. And you can, so if the power spectra all look the same, then you have a spatially stationary signal, and your sort of assumption of using the same filter coefficient every location seems somewhat reasonable. So you can see that it's sort of true. It breaks down a bit for things, in certain settings, like for example, you're looking at landscape scenes where typically the top of the image will have sky and the bottom parts won't. And it's worth noting actually that there are 1 or 2 cases you see of deep nets which don't use convolutions in some layers. So this is actually was the Facebook face recognition system a few years ago. Yaniv Tagman and others designed this. So this actually was interesting in that it had some kind of spatial normalization procedure at the input of the network. So the network always got a face that was aligned into some canonical reference frame. And it did a few layers of convolution, non-linearity pooling, but some of the later layers here had local connectivity. So they didn't use the same filter for different spatial locations. They would have and the reason for that makes sense in the sense if you're trying to analyze the eyes, you don't want to be using the same sort of filters as you would use to analyze the mouth, right? Whereas if you use a convolution, you would be using the same template for both locations. And you can get away with it because you've got the spatial alignment that's already been done for you. Okay, so just to make the point, you don't have to be using a convolution in the models. Okay, so right now, each element in those feature maps is going to be passed through some kind of nonlinear function. So this is, it's a 1D function. So the most popular one that people tend to use is something called a ReLU, rectified linear. So this basically, if the input is positive, then it's a linear function. If the input's negative, it outputs 0. There's a per feature map bias. So just see that in action. So there's your input feature map from the convolution. You push it through this thing. This thing's going to clip out the negative values. So you lose all the black elements basically in this. And there's a per feature map bias, okay, which is shared across all spatial locations within a feature map that effectively translates this function to the left or to the right. And that's going to be learned as well. So it can learn sort of, how much of signal it wants to preserve in the feature map after this operation. So people like this particular nonlinearity because if you think about when you backprop through this, all you have to remember is, it turns out if you look at the backprop equations, you actually have to know the derivative of this function, and the derivative is either 1 or 0. Okay, so that's very easy to store in memory, and so you can make backprop a lot faster than using some of the other functions that people think about. So these are the classic ones were things like sigmoid or tan h, which for various reasons, tan h, work okay, but the ReLUs seem to work actually pretty well if you just, these days. So I think a lot of this is sort of empirical, why you should choose one function over the other. One slight problem with the ReLUs, I guess, is that you get no gradient signal down here. So if that unit is in this region, there's no gradient to sort of pull it back to be active again. So one slight change you can make is to kind of have have this thing not be actually 0, but some sort of function which is sort of very close to being some very shallow slope here. So you do get some kind of gradient signal that can pull that unit back into play. So it's not dead forever. But I should point out that most people just use the standard ReLUs and so on. Okay, so for the pooling, what happens here is you're going to define beforehand a spatial sort of grid over your feature map. Typically, they're sort of much smaller than I've drawn here, sort of 3 by 3 or 2 by 2 regions, which usually end up being overlapping. I've drawn them non-overlapping here just for ease. And the idea is you're going to take within that region simply take the largest element or the average or something like that. Now, typically, everyone these days uses the max. So if you do that, this is taking this image and doing a 3 by 3 max pooling over it, and you end up with this sort of signal. So just to be clear, this is happening within a feature map. There is actually a variant of pooling that people did explore. Sorry, this is just to show you that you can also have overlapping windows for pooling as well, if you want. So one thing people did try, actually, was also pooling across feature maps, which you can also try. So but this involves pooling both spatially. So you would take, this element here would correspond to sort of pooling over this region and this region too. So something called max-out networks, which did get some very good results on some simpler data sets, but I've never seen them really apply to kind of ImageNet style things and so on. So intuitively, what's pooling trying to do? Well, pooling is going to give you invariance of small transformations, right? So if the object deforms slightly, as long as it's still within the same, that little pooling region, that 3x3 region, then if you're just taking the max over it, it's not going to make any difference to the output. Okay? And then the other thing to remember is, of course, as we pool, as we have multiple layers within the stages of pooling within the network, by the time you've done that several times, a single activation hypernetwork will actually be seeing quite a large region of the input image. Okay, so this gives us a way for the model to sort of learn these longer range correlations, right? Not just what's going on locally within small windows. So we can look at this in just a bit later on. These movies are some attempt to try to visualize the invariances that are learned by certain units high up in the models. This is essentially looking at a sort of the Hessian structure for a particular unit, at the input. So you're seeing basically these patterns all give the same activation at some particular unit in a network. Okay, so you can see this one seems to be some sort of scale invariance, and this one seems to be some sort of translation invariance that the network can learn. Okay, so you put all this stuff together, and the other thing I should say is that I'll explain it in just a moment when I talk about the optimization, but there are you do see there are some sort of techniques that try to then normalize the outputs across the different channels. So if you think about these operations, pretty much all of them have no kind of interaction. So that's not quite true. So you're doing everything here pretty much within a channel, right? You're convolving, and then you do this is just applied within a channel, and so is the pooling. There are some operations here which try to sort of normalize both across the channel and also perhaps across different examples within your data set, which I'll talk about in a second. And that gives you some output feature maps, which you're then going to plug back in to the next layer and do all these same operations again. Okay. Okay, now, so this is all very good and well, but there's a whole load of unanswered questions. So how deep should the network be? How many layers? How many feature maps should I have for in each layer? And then, how big should my receptive fields be? Or, how big should the filter dimensions be? And so on and so forth. And this is actually a point Jitendra was making, which I think also occurs to me as well, is that sort of before, in the pre-deep learning era, we were spending a lot of time just manually tuning good feature representations. But now, really, it's all about trying to figure out how to tune up all this sort of stuff, which is really the architecture of the deep learning system. And then you're just going to hope when you, set the backprop running that it's going to learn something coherent and sensible. Okay, so how do you actually go about choosing this? Well, I have to confess, I think most people really, it ends up being a mix of sort of intuition and just sort of trying a whole bunch of things randomly. Okay, so I thought it'd be nice if there was some deeper intuitions that would guide us in sort of which architectures we should try. But in practice, it ends up being an awful lot of just trying a whole bunch of different things with a lot of GPUs and seeing which ones work well. I mean, there are one or two ideas for doing slightly smarter strategies. Perhaps you can fit some sort of low-dimensional. You try a bunch of different architectures. You fit some sort of low-dimensional. Some low-capacity function like a Gaussian process or something to the different results in some sort of hyperparameter grid, and then you try and sort of guess where the next good hyperparameter configuration would be to try. And these things, I mean, people have released nice. They show nice examples in their papers, but I'm not really aware of anybody discovering kind of any profoundly new idea with these kinds of things. Okay, so now there's obviously a bunch of different things you can vary here, but I think the most important one, and of course it's in the name deep learning, is this, the depth of the model. And how important is it? So is it just, maybe it's just a proxy really for capacity. If we just had more parameters, maybe we'd do just as well. So we're going to do a little ablation study that looks at this kind of issue. So this is actually the architecture of the Alex Grzewski's model from like 2012. So essentially this input image, you've got a conv. I'm not showing the non-linearity, the ReLU non-linearities here, but each layer does have a ReLU in it. So you have a conv ReLU pool, and then conv ReLU, conv ReLU, conv ReLU pool, fully connected, and then you go to this softmax output to predict your 1,000-dimensional, one vector over the object classes, okay? So this was the model that they trained. So when they, just a single model, so they did do ensembling where they took a bunch of models and averaged, but a single model gets about 18.2% top 5 error. When we re-implemented it, we got basically the same. So what we did in this little study was to essentially knock out different pieces of this architecture, retrain the model from scratch, and see what happened, okay? So, in some sense, we can just, we want to break the model, so let's just see, which bits we have to remove to kind of destroy the performance. Okay, so one obvious thing you could try is just, do we need these fully connected layers, okay? So you can take one of them out, you can retrain. So you've just thrown away 16 million parameters, which is a good chunk of the parameters in the model, but it basically makes almost no difference to the performance that you get. Okay, so you say, okay, well, what about if we throw out both? Well, now you've thrown away 50 million parameters, so that's, I think, about 80% of the parameters in the model. And yes, it has gone down a fair bit, but it's still actually better than a lot of the classical vision methods.
When you say 5.7 drop in performance,
yep.
It's not adding 5% to the previous error. It's 5.7 out of the...
So
what do you measure the...
So it was 18.1 plus 5.2
okay. So
percent error.
Yeah,
okay. So, sorry, 5.7, not 5.2. Okay, and so, but still it's doing okay. I mean, you haven't completely broken the model. It's still actually doing something reasonable, even though you've kicked out of it. So if it was really an argument about capacity, then, then you surely would expect a sort of much more dramatic drop off there. Okay, so you could say, okay, well, the magic doesn't seem to be up here. What about down here? Well, you can now stick these back in, retrain these guys, so remove those extra convolution layers down below. Okay, so still seems to work okay. So you haven't removed that many parameters, right? Because the convolution is very efficient. You're showing those parameters across different spatial locations. You've lost 3% performance. Okay, so now, okay, so where's the rabbit? It's not in either of these two locations. So you can try. Now we take out all of them, the group down below and the group up here. So I've tried to keep the architecture generally the same, right? So I've tried to preserve the pooling layers. So now you've thrown away more or less the same number of parameters that you threw away up here. But now you've really broken it, okay? Because there's only actually 4 layers now between the input and the output. But you've now, the performance really has suddenly dropped off, okay? So you have roughly the same number of parameters as you had in this case, but you've got a much, much bigger decrease in performance. So it really is the fact that you have just not enough, you need to have lots of non-linearities basically between your input and output. And with 4, that's just not enough to be able to do well on ImageNet, it seems. Okay, so and I'll show you some more examples that get to this. So one little case is you can try just tapping off the features here of different layers within the model, and you see that this is just taking the features from, say, layer 1, pushing them into an SVM and trying to predict the class labels. So you can see nice sort of consistent gains throughout as you go up through the model. This is also some little experiments we did where you take an image and you try applying various transformations to it. So you can see this is just translating vertically. So this is the original image, and you can sort of shift it down or shift it up, and you can present that to the model. And you can see, you can look here, you can basically compare the feature representation I get at the first layer with no transformation to the transformed version. Okay, so if the feature representation was completely invariant, you'd expect those two feature representations to be the same, and you should end up with sort of 0 on this axis. Okay, so this is some sort of inner product between the two. But you can see at the first layer, it's really very sensitive to this vertical translation. Okay, you see very quickly that the feature representation changes. But by the time you get up to sort of the higher layers of the model, layer 7, somehow this whole thing's being kind of linearized. So now it's much smoother behavior. And indeed, when you now go to the output, the classifier's got a much easier time of sort of digesting the signals from here. And sure enough, you see that for quite a large, for these classes, the thing's pretty invariant now to different transformations of the input. Okay, so that was just translation. This is scale invariance. We see much the same story, right? So scale invariance, as we start scaling the image, very quickly the feature representations differ. But at the high layers, now suddenly it's been, it actually almost looks like a sort of linear a fairly gentle roll-off, basically, of how the feature representations change. And sure enough, we can get reasonable scale invariance. So I guess the point I'm trying to make here is, you do need some sort of complexity in your model to be able to sort of unpick these very nonlinear transformations that are occurring to the input, in trying to sort of straighten them out so that your classifier can actually have a reasonable chance of succeeding. So I'll skip over this in the interest of time. This is just showing the same thing for rotation. Okay, so as a result, if you now look at the work that followed on from Alex's original paper, they've all gone in the direction of just increasing the depth of the models. Okay, so this was some work from Annealing's group. What they've done really is to take what was a single 7x7 convolution in Alex's model and break it into a series of 3x3 convolutions followed by a ReLU. Okay, so now if you stack these 3x3 convolutions, you end up getting the same essentially spatial extent as a 7x7, but now you've got all these ReLUs in the way. So you've actually got a much more powerful function for the same sort of size receptive field. And so so they started off using a model with 11 layers, and then the biggest variant they have has 19 different layers in the model. Okay, so this thing actually is a pretty huge model. They did actually keep a fully connected layers at the end of the network, and this thing did actually get pretty impressive performance, right? So this thing got down to about 6.8% from 16% with Alex's model. Okay, so this is going from 7 layers to 19 or something like that, and then around the same time, Google produced this thing called an inception network. So this thing's a little bit complicated to understand, but this is a sort of chart of the overall thing. So this is the input image over here, and then the output's this over there. And they did actually have a sort of bunch of convolutions at different scales at each layer. So each layer is really one of these blocks here. So this is 1, 2, 3, 4, 5, 6, and so on like that. So they really, you can see, but you can see there's a huge number of non-linearities here between the input and output, compared to sort of earlier models that were relatively shallow. So this one was designed to actually have relatively few parameters in, and you can see, but so it's the capacity of this thing is actually a lot smaller than the original AlexNet paper, which was like 60 million parameters. It's only 5 million here, but you can see it's much deeper, and they're getting just over 6% error rather than 16%. And then I guess the final sort of the most recent paper things are something called residual networks. So this was the observation that if you just keep increasing the depth, well, what happens? Well, with 20 layers, things work pretty well. This is Tron training. Your training error, you can get pretty low training errors. But if you keep making them deeper and deeper, say 56, weird things start happening. So for example, if you have the 56-layer model, this is like a VGG net style. This is the VGG net style model from Oxford, just made deeper. The training error should be lower, right, because it's got more capacity. But it's not what happens. It ends up being, the training error ends up being higher. This is nothing to do with overfitting, right? Because this is just about training, and the reason for this is really somehow the optimization problem just gets harder as you have a bigger distance to backprop through, okay, from the output back to the input, and you end up with this problem of sort of the gradients vanishing or exploding and things like this, and what Kai-Ming He and others at MSRA came up with was a sort of alternate sort of variant of the model, where essentially you're going to, instead of just passing the signal in through some sort of weight matrix, ReLU, and so on, you're going to have a sort of bypass operation where you basically copy the input to the output, so that the bit the model's learning to do is just really a sort of essentially a kind of residual correction to the original input. That's what this piece here is doing. Okay, and so it turns out that this immensely improves the conditioning of the optimization problem that you're trying to solve, and means it becomes practical now to really backprop through hundreds of layers of model, okay? Because essentially you've always got this sort of identity connection in place, right? And the identity is going to have good conditioning. So this is just showing the biggest VGG model here, okay? And then this was their 34-layer model without the residual connections, and this is the one with, okay? And so they actually, I think, went to, I think they're, right, so their winning entry, this was 2015, I think, on ImageNet was just over 4%, 3.6% error, and this was 152 layers of this sort of thing. Okay, so again, what's interesting is the models don't have that many parameters, right? Each layer here has 3x3 convolution kernels, so very small filters, 64 channels. That's 9 parameters. Well, no, it's more complicated because it connects to the previous one. So this will be, I guess, 9 times 64 times 64 with the number of parameters in each layer on this one. In other words, it's not really about the parameters. It really is about the depth of the model. And so, yeah, sure.
You're passing through the identity, but the weight layers, are they initialized to random values?
Yes, I believe so. Yes, that's right. Yep.
Had anyone tried just initializing the center value to 1 and random elsewhere?
That's a good question.
That's not the question. Initializing what?
So basically the
Yeah.
right? So maybe it's just that the
Yeah.
random weights don't, you know, you basically, you're in a horrible
Yeah.
direction you have to learn from, whereas if you put a strong one in the middle and then small random weights elsewhere, it would kind of diverge from a pass-through, but it would just...
Yeah, it's a good point.
progress
It's a good
whatever
point.
it
I mean, Kai Ming's a pretty smart guy, and I'm sure he must have thought about this. But it's true. I can't, unfortunately, I don't know. I do have a slide deck from him, which I can dig through. Yeah, okay. Yeah. So just to show you, this is a similar graph to the one I showed previously, but this is for object detection, so localizing, putting bounding boxes. This is Kai Ming made this figure, so it's actually, the time direction flows in this axis. So it goes from right to left. Yeah, okay. So this is detection performance on, I think, this is detection on ImageNet. The ImageNet also has a detection competition, not just a classification one. Oh wait, I'm sorry. This is actually, I've got the wrong slide. There is, says classification top 5 error. Whoops. Okay, I'm sorry. There's an analogous one that shows the same trend, but for detection performance. But I've taken the wrong slide, which is basically for the classification. It's the same as before. Okay, so one thing I do want to talk about, one of the big problems here, so these networks work very well, but how do we know what's going on inside them, which is, I think, the sort of perennial problem. So if you want to know what they've learned, in the first layer, you can just look at the filter coefficients, right? That the filters are directly interfacing with the image pixels. You can just sort of inspect them, and this is the kind of thing you see. So you see nice color opponency, low frequencies, and then you also see sort of high frequency grayscale gabors and things like that. But the higher layers are much more difficult to interpret, right? Because they're taking in, they're not looking at pixels. They're looking at the feature maps in the previous layer, which are some very, very nonlinear function of the input. Okay, so there's 3 rough techniques you can use to sort of have a look at what's going on in these upper layers. The simplest one really is just to look at image patches that gave you strong activations in a given feature map. So I'm going to look at these each in turn in detail. So the second one was to take those strong activations and have some technique for kind of projecting them back to pixel space to see what they actually might be doing. And then the third one is to sort of, if you want to know what a particular feature map's doing, you can try and find input, do gradient descent to try and maximize a particular activation or in a feature map. All right, so let me just go through each of these. Okay, so the basic idea is you're going to take your validation set. You will, in one image you put in through your network. Say this is these. You want to understand what goes on a particular layer. For each filter in this layer, you have a corresponding feature map. You are going to take a validation set of images. So you're going to push a whole bunch of images through. So you have a whole bunch of copies of a given feature map. And then the simplest thing to do is just to take. Whoops, sorry, my animation's a bit crazy. Is to take a particularly strong activation, say in one of the channels here, and you get this is the strongest one over the whole validation set. And the idea is then to just the receptive, you can figure out at that location what's the corresponding image patch, and so the sort of center pixel, and you can work out the spatial extent by knowing how many sort of pooling layers and the dimensions of the convolution kernels and stuff like that between the input and this particular layer. Okay, and if you take not just the single strongest activation, but a whole bunch of them, say the top, 9 or so, that can give you a sort of non-parametric feel for what that particular feature map's capturing. So just to look at this in a bit more detail, so here are the filters for each in your first layer, and these are the image patches that gave really strong activations in the corresponding feature map. Okay, so if we just, sorry, I'm going to stand the right way here. So if we take, this is a subset of the things. So I think, for example, this one here, if you look up there, so these are all, just sort of oriented edges, and you can see this. These are sort of 9 image patches that cause the feature map that corresponds to this filter to have a really strong activations. Or you can see this one here, this sort of green filter. Well, sure enough, the image patches tend to be kind of green. You'd expect that. But now if we go up through the model, you start to see some interesting things. So this is now layer 2. So you've had 2 layers of pooling. So the receptive field is larger now when you project back to the input. Okay, so now you're looking not just at sort of simple edges, but sort of conjunctions of edges. And you start to see feature maps that really seem to select out, circular structures, textures, sort of fur or something like that, and so on. And you go up to layer 3. This is a sort of Alex Grozevsky style model. So this thing's got about 5 convolutional layers. So at this point, we're kind of at the object part level. And you start to see some sort of semantics starting to be visible, right? So you start to see, interestingly, this one seems to pick out text on objects. Or this is like still seems like circular structures. This one seems like people's faces and things like that. And then layer 4 and layer 5, the receptive field is pretty big now. Okay, so it's pretty much covering most of the image, and you're seeing really a lot of sort of object-specific feature maps are occurring. So just to look at, say, for the top one, for example, this one's likes computer keyboards. And what's kind of funky here is that there was no sort of inherent rotation invariance in the model, but you see that this feature map seems to be somewhat invariant to the orientation of the keyboard. Okay, and you're getting that because of all those non-linearities and pooling operations that are taking place. And you're seeing, there's lots of dogs, of course, in ImageNet data, so you see lots of feature maps. This one seems to specialize in sort of huskies. This one seems to like, I don't know, smaller sort of fluffy dogs and things like that, and so on. And then one sort of refinement of this is, whoops, sorry, my animation's slightly whacked out, is that you can do the same principle, but instead of just sort of looking at the image patch, you can have some attempt to kind of reconstruct, sort of project back down again this activation using the filters in the model, sort of in some sort of, it's not technically really an inverse, but some sort of reprojection down through the model. And there's a whole bunch of different sort of ways of doing this that are sort of really somewhat similar to one another. So this is just showing what, one particular one we did. So this is the corresponding image patch. This is just showing if you do this reprojection, it effectively tells you, which pixels in that patch really mattered to the model. Okay, so for example, if you look over here, you see a whole bunch of little examples of with text on. But if you look at this, the reprojection down to pixel space from those activations, you start to see that in fact the network doesn't really care about the color or the background or anything. It's really caring about the text itself that's on the bottle, and that's what's causing the feature map to trigger. Also, for example, here, this sort of mesh-like, these grid-like structures seem to be what matters rather than the color or of the object or anything like that. So you can see some quite funky things. Like if you look at the ones down here, it looks like you see sort of seaside scenes, and then you see, if you do this projection, you can see in fact it's the water that's really causing the thing to fire. It doesn't care about the foreground object, which probably has much more spatial energy than the actual water itself, but somehow the network is able to select the water rather than that. Okay, so the final technique you can use is to sort of maximize, optimize your input to maximize a particular output. So intuitively, all you're doing here is just backpropping through the model all the way now down to your pixels. So normally, of course, you hold your input fixed, and then you just backprop. When you backprop, you're just updating the parameters in each layer. Now you're going to backprop all the way to the image and update the image itself. And you can do that in such a way to sort of choose to maximize, say, the banana output. So if you start off with random noise and you backprop on your input image, this random noise, to maximize that banana output, then you start seeing sort of weird banana structures. And the Google Deep Dream just tweaks this idea by kind of adding a slight prior that you follow based on sort of image statistics, simple image statistics models. And you can get sort of funky patterns like this, and you can sort of apply this kind of recursively at multiple scales and so on. You get these kind of crazy hallucinations, which I'm not sure exactly what it tells you about the model, but it looks cool and things like that. Okay. Okay, so I just wanted to say a few words about training big ConvNet models. So the prevailing paradigm really is just to do gradient descent. Now, the catch, one slight twist is that instead of computing your gradients sort of averaged out over all your training set, which is like millions of examples, what you're going to do is to sort of do a sort of quick and dirty version of it, where you're just, instead of waiting for you to compute the gradients across all a million and then average, you're just going to take a small batch, like say 100 images or something like that, compute your gradients for those, average over that small batch, and then just make a step. Okay, and so the idea is that, of course, that gradient direction will be noisy with respect to the true gradient, because you're only averaging over 100 rather than a million, but it sort of doesn't matter in the sense that the surface is highly curved and very nonlinear, the objective function you're optimizing, and so it's better just to take lots of quick steps, because if you compute a really accurate gradient, it's going to be completely wrong once you've moved to the new location anyway. So you might as well just get a rough direction, move there, and then recompute with the next batch of data. And so in practice, this is the sort of way people have trained things. The basic idea is to just have initially a pretty large learning rate. So that is, you'll have a sort of large step size on the gradient, so large scalar value, and then you'll just reduce that as you go. So it's a diagram that I should have included, but I didn't. One thing that people do tend to find consistently works well, there's 1,000,001 tricks. There's a whole giant literature now of sort of tweaks to make your deep learning thing run faster in training. One thing that people do consistently find helps is usually some kind of momentum. And there are sort of various types of momentum, but momentum usually tends to help you out. So the training is going to look something like this. So this is just showing, this is validation performance, sorry, not test, this curve up here, but the solid one is your training error. What you'll notice is you start with some large learning rate, you'll run, you take, do your stochastic gradient descent, and you'll, make good progress, but it'll start to flatten off. And then what you'll find is if you just reduce the learning rate by some factor like, factor of 3, so it might be sort of 0.1 or something here, and then it'll be 0.03 for this section, you'll see a really quite dramatic decrease in error. Okay, so why is that? Well, I think the intuitive explanation, which I'm going to have to draw a little picture instead of having on my slides, is that the energy surface has multiple scales attached to it. So obviously I can't draw a 60 million dimensional energy surface, which you would have for AlexNet, but just to have a 2D version, the idea is you would have something like, it would be like this. So in this direction, the curvature is very tight compared to this one. And if you have a large step size, essentially you're going to sort of, you might be able to optimize in this axis. So you can optimize to this thing fairly well, but you'll oscillate sort of back and forth basically in this one. Your curvature is too tight, you can't drop down to the valley. But if you reduce the step size, then suddenly you can sort of access this dimension, and you can optimize that. So that's the sort of hand-wavy kind of intuition. So if you do this carefully, you can actually consistently get really quite substantial drops in performance. And of course, once you get down here, your learning rate's pretty tiny. You're probably not going to make too much more progress. But this annealing of the learning rate seems to be a very useful thing to do. And just to show that this is just using some of those visualization techniques at different stages of training to see what it is that the filters are doing. So initially, you see that the filters are, in the first layer, actually, even after one epoch, they're starting to do something sensible. And by sort of 3 or 4 epochs in, they pretty much sort of converge to something sane. But you see that sort of it takes a little bit longer for these ones at layer 3 to actually do something. And what's interesting is when you get to the sort of higher convolutional layers, it really does seem to take quite a lot of epochs to get sensible structure being picked out here. In other words, so of course at these points you really anneal the learning rate quite a lot. So for this epoch, the learning rates are very high, and these ones it's much lower. So in some sense, these layers of the model seem to be optimized much more effectively when your learning rate is smaller. And so, of course, this is incredibly clumsy and hacky, sort of manually tweaking this learning rate. So there's a little cottage industry of sort of adaptive learning rates out there. So you can, a whole bunch of different recipes. So I guess Adagrad is probably one that's most well known. The idea is, this is your scalar learning rate. You're going to have some denominator which basically will slowly increase over time. That's the kind of idea that you're looking for. This is the gradients that you've computed through backprop, and this is the actual update to your model parameters that you're going to be making. The slight catch is, of course, with this kind of thing is that this is a monotonic increasing term. So this will sort of ultimately sort of stop you making progress beyond a certain point, and so on. But anyway, there's a whole sort of little recipe of doing this. Usually, the key point is that people are trying to usually compute this update without touching second-order information. Okay, so the problem is that in these networks with millions of parameters, that, if you have a 80 million parameter model, your Hessian is 80 million by 80 million. Okay, so you can't even store it. Even a diagonal approximation is going to be somewhat painful to compute. Some of these ones do rely on that. There is some efficient way to compute the diagonal elements of the Hessian. There's something called an R-prop operation that does exist in the literature. And so this is the reason why, actually, whoops, sorry, I'll come back to that slide in a second. This is actually the reason why second-order methods really haven't prevailed at all in this field. So if you've done an optimization class, most of it is actually there's a huge amount of focus on things like getting second-order information. But the problem here is that usually it's so expensive to get that basically you might as well just take more dumb steps with your... you're computing really accurate curvature information at your current point. You might as well just, it's going to be completely out of date once you move just even a small distance. So you might as well just stick with your standard first-order stochastic gradient descent. So, but there are some interesting papers that people are trying to do things in that space, not getting too far. One thing that does seem to help quite a bit is this trick called batch normalization that the Google folks came up with. The basic idea is you're going to sort of try and normalize over your batches. The idea is that different batches of data will have different mean and variance. And that's somehow very difficult for the subsequent layers of the model to handle if somehow the distribution's kind of jumping around the whole time. And this is an attempt to effectively you compute the sort of per batch mean. This is a vector. So this is your sort of feature map elements just in sort of vector form. You compute a sort of a per dimension mean and a per dimensional variance. And you use those just to sort of, center the distribution and rescale it so it's unit variance per dimension. And that actually seems to help quite a bit. So this is some training curve they're showing for that big Google Net model I showed earlier. This is the interception curve in black without this normalization trick. And if they do this kind of batch normalization, then the convergence is much faster. They do actually seem to end up with slightly better performance as well. And this is a trick that does seem to hold out and work quite consistently well. So this was the purple box that I was alluding to earlier when I was showing that overview of what goes on. One fun thing I did want to talk about while I'm on the topic of optimization. So, one of the classic objections to deep nets was this idea that they weren't convex. There were going to be all these local minima. How do you know the local minima is any good, and so on and so forth. So this is a very simple. This is an exploration of that topic, admittedly using a very simplified model that's nowhere close to the complexity of this kind of thing you would use for ImageNet. So what they did was to take, I think it was just like 2 hidden layers. They're doing sort of MNIST or something like that. And what they did basically was to take a whole bunch of models with different initializations, okay, and then train each one separately, and then do a histogram of the losses, okay. And so what we see in the yellow, for example, is when you have 25 hidden units per layer, you see quite a distribution over the losses you end up at, and that's not good. That's telling you that the sort of best model, which has the lowest loss on this axis, is really a lot better than the worst model. So that's sort of saying, well, it's not a lot better, I guess. So the scale is somewhat compressed here. But the point being that somehow, the fact you see a spread of this distribution tells you that there is a difference in energy between the best minima that was found and the worst minima that was arrived at during training. But what's kind of interesting is that as you make the model bigger, and so, as you see here, increasing the number of hidden units, this distribution, well, 2 things happen. First of all, it moves to the left, which makes sense because you've got more capacity. You should be able to get a lower training loss. But the other thing that happens is that the variance reduces as well. So it's telling you that somehow these minima are becoming more and more equivalent to one another. Okay, so this is sort of empirically seems to be backed up. And when you take your ImageNet model and you just train it, you do seem to sort of end up, it's rare, you don't end up with a model that's sort of got twice the error of the other one. Okay, the error rates seem to be somewhat close to one another. And that's sort of a reflection of the fact that you have a sort of fairly tight distribution when you have these more complicated models. So I think this is quite an interesting. It was an empirical thing, obviously, but I think there's a lot of interesting theory that people are trying to look at as to why that should be the case for these. I mean, it's basically to sort of over-parameterization of your model. Maybe that helps the optimization procedure, escape from kind of really weird local minima. Okay, so one thing, of course, you still have to worry about is, overfitting these models. They're very big. The classic sort of tricks are like augment your data. So you can take your image, you can kind of make perturbed copies. Like you can translate it slightly, you could scale it slightly, rotate it slightly if you think that rotations are important. So that consistently seems to help. Usually, a little bit of weight decay can often help too, particularly on fully connected layers at the top of the model. That usually will help prevent overfitting there. Weight sharing, of course, always tends to help, but convolution layers do that for you automatically. You can end up doing it if you've got some sort of multitask learning. That's another way of thinking about weight sharing. You've got some common trunk, and you have different heads. One head might be doing face recognition, another image classification, and so on. And you can sort of share the labels that you have across those 2 tasks, within that trunk of the model. And then also the trick of there's another sort of slightly less intuitive thing which can help, which is injecting noise into the network. So the dropout is the most common one. So this is basically a form of kind of stochastic noise. Basically, you can think about this as a sort of, you're randomly going to delete or set certain channels in the output of each layer to 0. Okay, and then you're going to sort of, so you can think of just adding a sort of, shot noise basically to your feature layer output. And then when you do backprop, you have to remember which channels you kind of deleted. And then you have a different sort of noise pattern for each example. Okay, and this is just during training. And at test time, you sort of don't do this. You just sort of average. Basically, you just forget about the fact you train without this noise, but you just have to rescale because the next subsequent layer would expect to see a sort of smaller magnitude of input. The basic idea, what this boils down to basically, is it's a funny form of ensembling. So the idea is that each configuration of these deletions corresponds to a different sort of model, different version of the model. And when you're at test time, you've got a sort of basically a sum over all these possible combinations. And in practice, it does seem to help quite a bit. This trick, I have to say, really works well for fully connected layers. For convolutional layers, there are analogous versions of it, which help a bit. But the truth is, if you have enough training data, you don't need to bother with these tricks too much. Particularly if you've got these more things like the ResNet and the Google Net and things like that have been much more sort of parsimonious with the parameters, so that they don't tend to overfit quite as dramatically as they did before. So here's a little intuition about, so one thing you might say is, why do we bother with the regularization? Why don't we just make the neural net smaller, and then we won't have to worry about overfitting? So here's a little sort of argument why you want to have a big model and then regularize it, rather than just going with a small model. So if you have the small model, you can fit, your data reasonably well. I mean, you lose fidelity in these sort of high density regions, but it doesn't do anything insane in the low density regions. Okay, and then if you have a big model, well, it captures the structure nicely in the high density regions, but then it starts going a little bit nutty, outside where there's no data to constrain it. And so the idea is that if you have the appropriate regularization, then you can, with a big model, that's really going to sort of make the biggest difference to the decision surface in these low density regions. So it'll stop the model doing anything too nutty over here, but hopefully where there's data to sort of support what's going on, then it'll still retain the sort of structure, and the regularization won't perturb it too much from what it would have been. Okay, so that's the sort of rough hand-wavy thing. Okay, I'm getting a bit short of time, so I'm just going to skip over a few things. So there's a few. Okay, I'll try and do this quickly. So these are just some sort of practical hints and tips for getting your net to train. Okay, so first thing to do is check your gradients. Right, you're going to update your model parameters by backprop. You're computing these gradients for each parameter. If your analytic gradients are wrong, then sure as hell it's not going to do anything. Okay, and so most of the modern deep learning packages sort of hide this from you. They've already, the backprop operation is kind of automatically built in along with the forward prop, so you don't have to worry about this. But if you're implementing a new module, a new sort of type of layer, you should definitely do this. And you definitely want to sort of visualize the unit. So this isn't using a sort of for a fully connected network. Just this is you've got a vector of hidden units at each layer, and this is just for different samples. You want to see sort of you want to see something like this, right? Sparse activations that are sort of uncorrelated with one another. If you see things like this, then you're in trouble. Okay, so that means that somehow the model's just responding the same way to different input examples. Okay, which means that it's kind of ignoring what's going on. If you look at the filters, you basically want to see sort of diversity in the filters, not some sort of high frequency junk or some sort of weird things. Of course, what's a little bit hard is to know, when you see this, something's wrong, but it's a little bit hard, I will still say, to know which knob do you need to tweak to actually sort of fix things, which of course is what you really care about. And that's, so one sort of systematic way to try and isolate the problems a little bit. So you can, of course, you should measure error on both your training and your validation sets. You could just take a very, very small subset of your data and check you can minimize the training error, right? I mean, if you've got a tiny amount of data, your model should absolutely crush it and get the error to 0. If it doesn't, there's something wrong there. So if your training diverges, maybe your learning rate's too large, so maybe you should try doing that, or maybe your analytic gradients are doing something crazy. If you do manage to minimize your loss, but then your accuracy, so if you actually, the classification accuracy is a proxy, your training loss, the loss function you use is a proxy often for the thing you care about, say classification accuracy. If you can minimize the loss, but the accuracy is still terrible, then you've probably got the wrong loss function. Or there's some sort of degeneracy in it that lets it sort of, collapse to 0 while the accuracy remains high. If your network isn't doing very well, so that is, the training error is going down, training accuracy is going down. This is a slightly trite answer, which is, in true deep learning fashion. I should say I got these slides from Mark Aurelio Ranzato, who's a student of Jan LeCun's. So this is the classic deep learning response, which is if you're not getting good enough validation error, just make your model bigger, and then it will be well. And then if it's too slow, basically the advice is buy a bigger computer, which again isn't particularly helpful. Okay, so just to wrap up, the model in the last few years, the models have gone from being sort of interesting for people in industry, but not awfully practical, basically because of poor performance and expensive runtime. But now they really are used all over the place in industry. So I spend time at Facebook, and they're used for things like face recognition, finding offensive content, saying what's in the pictures that people upload, and so on. And so they can do that because, Facebook, I don't know the exact numbers, but they get at least half a billion images uploaded each day, and they're able to sort of crunch these with deep nets because at test time these models are just very efficient to run. Okay, so you can actually, with big GPUs, you can run hundreds of images through them in a second if you batch them up, and it's meant that it's practical now to run these vision as a sort of service that provides us sort of signals for other other parts of the company and stuff like that. And it is reliable enough that it really can be really can do things that are practical. And so yeah, so I guess I should stop there probably to have time for questions.